have to figure out, oh yeah, I have to connect this. So for example, question number 5, right? You have to do the loop invariant, right? And so the comparisons were going like this, not like this. So if they're going like this, right? So what's going to happen? The biggest number is going to go to the bottom first. For example, if you have some numbers between 1 to 10, and the 1 is the smallest, is here, when you go like this, that 1 is only going to go 1. Next time it's going to go 1 again. So, but the biggest number is going to go to the bottom first. So the loop invariant is that you're going to have everything sorted from some point here down to the bottom. So initially you have nothing sorted. So you have to have what? Out here, right? This value. And then you have 1 sorted, then you have 2 sorted, 3 sorted, and then when you do n minus 1 times, you have n sorted. So how many people got that correct? Let me see the hands. If you get that correct. How many people got the this way sorting? So you have to, so when you have an algorithm, a good idea is to take a piece of paper, give yourself an array. Don't make it 1, 2, 3, 4. You know, make it 7, 11, 2, 12. Make it different numbers, and then go through the algorithm, see what's happening. Walk through the algorithm to understand it. Because looking at the code, very few people can look at the code and say, okay, I know what it's doing. Okay, if you can do that, good. Good for you. Be happy. But most people have to experience the code, right? It's like when you're trying to do an exercise. When you're trying to raise something very heavy. Oh, I don't have to do it. I already studied it. No, you have to do it, because when you do it, that's when you'll understand how it really works, right? So you have to experience it. So algorithm is kind of an applied thing. You should be, oh, it's not showing again? Did we have this problem last time? Huh?
It was working fine.
Last time you did it was working fine? What is going on here? But for me, did I have a problem last time?
Yes, you did.
What's going on? I think Conveyor is fixing it so it's not working for me.
Yeah, now it's okay.
Yeah, but that's not my computer. Oh! Huh. All right, I'm a genius. I fixed the problem. Okay. Okay, how's this? Good? All right. So, let's go to the second part of the notes. Second part of the notes, we're going to be talking about algorithm analysis. So, we are talking about, when we're talking about algorithm analysis, we're not talking about performance. We're talking about order of magnitude. What do I mean by order of magnitude? What is order of magnitude?
Order of amount?
But what does it mean, order of magnitude? Yes, but so what's the difference? Give me 2 different orders of magnitude.
5 and 3.
5 and 3. Well, they're different numbers, but it's not order of magnitude. For example, you know scientific notation? So scientific notation, we have 1.765321 times 10 to the 18th power. Then I have 3.7123872 times 10 to the 13th power. Which is bigger? And so each time we multiply something by 10, we call it order of magnitude. So the 10 to the 18th power, 10 to the 13th power, we don't care about this. This is small. But the order of magnitude is, is it millions? Is it trillions? All right? Is it billions? Is it thousands? So that's what it is. So order of magnitude typically is like a function. A linear function, what does it look like? It looks like this. A quadratic function, what does it look like? It goes like this. But there are other complexities. There's logarithmic functions, right? What do a logarithmic function look like? It looks kind of like this. If I have a board, I draw it for you. Now I have to use an imaginary board, like this. Exponential functions, they go like this. How about n log n functions? What do they look like? So n log n is more than n, but it's less than n squared. So it's going to be between this, so it's going to be kind of like this, right? It's going to be still increasing more than linear, but less than quadratic. So order of magnitude means when you take limits of functions. And I really do need some board. I don't like this room because the board is so small. So maybe I will use a little bit like, can you see that? That's good, right? So, the important thing is that we have to understand limits. So if we take, for example, can you guys see that? The limit as n goes to infinity. Okay? For example, of n squared. What is the limit of n goes to infinity of n squared? What is the limit as n goes to infinity of this function n cubed? So the function, this function, as n increases to infinity, n cubed goes to infinity, right? Now, what about the limit as n goes to infinity, for example, of n squared? Does that also go to infinity? Yes. Okay, so that's fine. Okay, but now what happens if we take the limit as n goes to infinity and we have n squared over n cubed? Well, this is going to infinity, but this is going also to infinity, but it's in a denominator, so it makes one go to 0. So now obviously we can simplify this, but just think about it. This is going to infinity, and this is going to infinity in the denominator. So this is making the ratio go to infinity, this is making the ratio go to 0. But because this is a higher order than n squared, what happens is the drive to get the ratio to 0 is more powerful, and this limit goes to 0. And of course we can see that the limit of n cubed over n squared is nothing more than 1 over n. So now we see as n goes to infinity, this is just 1 over bigger numbers, that just goes to 0. So it's how quickly you're driving. So on the numerator, these drive the functions to infinity if they're increasing, and these drive the functions to 0 if they're increasing. If these are decreasing, then they drive the function to 0, and if they're decreasing, they drive the function to infinity.
Professor, I have one question over
Yeah.
there. Infinity itself is
Not a number.
Not a number. So
Not a number. It's basically, infinity is a concept of a number increasing without bound, always getting greater.
yes. So I mean, infinity over infinity. I mean, even if you take infinity plus 1, and that's infinity, right?
Well, first of all, no. Infinity, you cannot divide infinity over infinity, because infinity is not a number. So we'll talk about why that's the case. In some cases, you can sort of look at it infinity, like if you have something's going to infinity and something else is going to infinity, and you have a plus. Well, what's the sum going to? Infinity. But let's say this is going to infinity and this is going to infinity, but now you have a minus. Well, now you cannot say what it's going to be. And the reason you cannot say, because basically you're subtracting this. And if this is more quickly going to infinity, what's going to happen?
Negative.
Okay, it's going to go to negative infinity. But if this is more quickly going to, what's going to happen?
Positive.
Okay, so with a minus, we cannot do it. Okay, so don't worry about that. As we need to get into the details of this, we'll get into details of this. So I will go through it as we need to. And I may actually generate some extra notes for you guys on some of the math issues. Okay, let's see. So let's talk about complexity. So complexity means n squared. If you take the limit of n squared, it goes to infinity. If you take the limit of n cubed, as n goes to infinity, also goes to infinity, right? So let's consider an algorithm that has a complexity of roughly n squared. Now, what do we mean by that? Let's say bubble sort. We know bubble sort very well, too well. Some of us, just okay, enough bubble sort already, but we're just starting. So bubble sort requires about n squared statements to sort n elements. And let's say we can sort n elements in time t. T could be 1 millisecond, 1 microsecond, 10 nanoseconds. I don't care. Some time t. There is a time t. So when I run in time t, I can sort n numbers. Okay? I can sort n numbers because I can execute n squared statements in time t. Okay? So now, let's say I increase the computing speed by 1 million. If I increase the computing speed by 1 million, that means in the same time t, instead of executing n squared statements, I will now execute 1 million n squared statements. because 1 million times n squared is 1 million times more than just 1 n squared. So the question is, if I can increase it by 1 million, then my number of statements executing is 1 million n squared. So the question is, how many elements can I sort in time t? And the answer is, how did you get from sorting n, requiring n statements? Basically, we took the square root of the statements to get to n. So if we increase the speed by 1 million, that's nothing more than 10 to the 6th power times n squared, and the square root of that many statements is equal to 1000 n. So if we increase the speed by 1 million, the number of problems that we can solve is going to be 1000 times bigger. Does that make sense? So even though the computer is going 1 million times faster, this algorithm complexity, n squared, is only increasing the problem in the same time 1000 times, which is square root. That is the inverse function of f second power. So if the function is y is equal to, let's say we're going to say n squared, and so what we want to do is we want to take the inverse function. And the inverse function means that we're going to switch these variables. So what we're going to do is we're going to call this n, and we're going to call this y. So we have now y squared is equal to n. So that means y is equal to what? Square root of n. So the relationship between the problem size and the number of instructions for an algorithm that has an n squared complexity is the square root of the complexity, because that's the inverse function. If the algorithm required n cubed statements, then what would be the relationship between the number of statements and the problem size? It would be the cube root. Okay, good. All right. Now, we have an algorithm that we're going to study later in the semester. It's called heap sort. And we know that heap sort requires log base 2 of n statements. LGN is equal to log base 2 of n. So LGN is equal to some number. 2 to what number is equal to n? 2 is basically log base 2. So this algorithm requires LGN statements for n elements in a given time t. If we increase the speed by 16, then instead of executing LGN, we can execute 16 times more, or 16 LGN. How do we go from LGN to n?
Just multiply by 16 log n base 2.
So you can see here, so basically here, how do I get from LGN to n? How do I drop the n out from LGN to get n? I raise it
To the
power of 2. So if the complexity is logarithmic, the problem size is the inverse of logarithmic, which is exponential. So for example, let's say I have LG of 1024. That's log to base 2 of 1024. 2 to what power is 1024?
2 power 10.
That's equal to 10. That's equal to 10, right? So, if I take 2 to this power, what is that equal to? So basically, this exponent is 2 to what power is 1024? 10. So this is the power you raise 2 to make 1024. I'm raising 2 to it, so I'm making 1024. Inverse function. Log 2, exponential of 2. Inverse. Log 3, exponential of 3. Square root, squared. Cube root, cubed. Okay, these are exponential inverses. So therefore, since I can execute 16 LGN statements, but 16 LGN can be written as LGN to the 16th power, because log rules show that A constant times a log is the log of that number, the power of the factor. So it's LGN to the 16th. So therefore, that's the problem size, because basically that's the problem. So if it's logarithmic, it's going to be exponential increase. So the amount of speed up that can be realized for an algorithm by using a faster machine is proportional to the inverse function of the speed up. Inverse function of the speed up. So if the speed up is 1,000,000 and the complexity is quadratic, then the square root of 1,000,000 is 1,000. That's the speed up. If the algorithm has a speed up, it has a complexity which is quadratic, second power, and the speed up is by 16, how much bigger problem can I solve? 4. Square root of 16 is 4. If the complexity of the algorithm is cubic, n cubed instructions, and I speed up the machine by 8, how much bigger problem can I solve? Twice as big, because the cube root of 8 is 2. Okay? All right. Now, algorithm in which the problem size can be solved in a given time increase linearly with computing speed are called linear complexity algorithms. So for example, if I can solve a problem, for example, let's say I just want to add all the numbers in an array. Add all the numbers, so I have to just look at the numbers. So if I have 1,000,000 numbers, it takes me 1,000,000 cycles. So if I have 5,000,000 numbers, it takes me 5,000,000 cycles. So if I can speed up my cycles by 10 in the same time, instead of looking at 1,000,000 numbers, I can look at 10,000,000 numbers. So the speed up is 10, and the algorithm problem size increases the same, because the inverse of the linear function is a linear function. Okay? Okay, this is a chart that sort of sums up what we're talking about. So basically, if the problem size is n, and the approximate instruction count is n, then if the speed up is increased by 1,000,000, that means it's going to be 1,000,000 times n, or 10 to the 6th power n. The new problem size is going to be 1,000,000 times n. The problem size increases by 1,000,000. But if it's quadratic, the inverse function here is square root. So n, approximate instruction count is n squared. So speed is increased by 1,000,000. So instead of executing this many instructions in time t, I can increase by 1,000,000 times n squared instructions. So the square root of that is 1,000n. So you can see the square root of this is going to be n squared. The square root of this is going to be n. Okay. Logarithmic, same thing. If the problem size is n and the approximate instruction count is logarithmic in time t, then if I increase the computer by 1,000,000, then it's going to be 1,000,000 times LGN instructions at the same time, but that's LGN to the 1,000,000th power. Okay, so that means it's going to the size problem is going to be now n, whatever it was, raise it to 1,000,000th power. So it's good. So if it's logarithmic complexity, when you speed up, you get crazy speed up. Exponential means that this is the same problem n. In time t, I can execute this many instructions. So if I increase the speed by 1,000,000, I'm going to have 1,000,000 times 2n, because that's the number of instructions, right? 1,000,000 times 2n. But 1,000,000 is about a meg, which is 2 to the 20th. So 1,000,000 times 2n is about 2 to the 20th times 2n, which is 2 to the 20 plus n. So that means I can now, the new problem size is only going to increase by 20. If I speed up my computer by 1,000,000, I can only solve a problem 20 bigger. We don't normally increase the speed of a computer by 1,000,000, but it shows you that even if you could. So if you have an algorithm that has an exponential complexity, it's very hard to increase solving bigger problems, because it's going to, in the same time, you can only do very little more.
Professor, to make any algorithm more efficient, you should always aim for logarithms technically by this.
Well, if we can find it. And of course, many algorithms, we don't have anything better than exponential. Or we don't have anything better than quadratic. We'd like to have linear. Linear is nice.
Linear is always the case.
Linear is always nice. This is wonderful, but can't always do it. Because let's say you want to add up the numbers for an array. If you want to add up all these numbers, is there any way we can add up n numbers without reading n numbers and doing n additions? So you cannot reduce it to logarithmic, but linear is pretty good. That means we only visit something one time. Okay. All right, so let's take a look at some of these examples here. So what I have here is, so we talked a little bit about complexity. Let's go back to a simple concept called instruction count. Instruction count is if you have this bubble sort algorithm, you're going to go, it's very similar to the one I gave you on the homework. 1 to n, 1 to n minus 1, 1 to n minus 1. So that means, why only n minus 1 on the outside? Because if you do n correctly, then the last one is already there. So that's why. And why do we do here 1 to n minus 1? Because 1 to n minus 1, the last n minus 1 is always compared to the next one. So when j goes to I minus 1, n minus 1, this is n. So we hit it. Okay, so basically, so it's line number 1, 2, 3, 4, 5, 6. And of course, is if they are out of order, we do the swap. Swap means we have a temporary, then the xj takes the other, and the other takes the temporary. That's the exchange. So 3 instructions. So if we look at the first statement, I'm going to say it executes n times. And the reason it says n times, even though it says 1 to n minus 1, is because when I is equal to 1, we go in, 2, 3, 4, 5. All of a sudden, n minus 1, we go in, and then I has to go to n. We test it, and it's too much. So that test is also an instruction. So therefore, instead of n minus 1, we're going to say it equals n times. Every time we go in from here to here, from statement 1, line 1 to line 2, we go in exactly n minus 1 times. Because we only go in n minus 1 times from the top statement to the second statement, because that's the value of I that's in the right range. So when we do go in, every time we go in, j statement executes n times. So that's why we have n minus 1 entries, and each time n times. So that's the number of statements for number 2. Number 3, we're going to assume that every time we go in here, we're going to do what? If xj greater than xj plus 1, so we're going to say this statement executes every time we go in here, we go in, and we go in here n minus 1 times. So we say n minus 1 times n minus 1. Yes?
The second statement says n into n minus 1, but then Professor, when the outer
Which one? Second statement. Yeah.
Second one.
Yeah.
So when the outer loop reaches n, like you said, it's a false statement, but still it will execute. But then it won't go inside the loop, right?
For the nth time.
Nth time it won't.
Yeah.
go inside the loop.
But we're not counting, the entries are counted here. We don't count the entries here, so this is just basically, so we test, okay, test, okay, test, okay, test, not okay. But that last not okay test is the nth test, is the n times we execute that statement.
Oh.
And then this one executes, we only go in from here to here n minus 1 times, and then each time we go in, we got to go n minus 1 and a testing statement, so it's n, so it's going to be n minus 1 in times n for the test each time.
Okay.
And this one, of course, means once we go in here, we are going in here n minus 1 times, and we're going into this too n minus 1 times, so it's n minus 1 times n minus 1. Now here, we're going to compare. Now if you notice, this comparison is saying we're basically going from, we're just kind of going like this, comparing, but each time we're comparing, basically, here, the biggest element is at the bottom, now 2 biggest elements, 3 biggest elements. So on the 4th pass, once I start comparing here, it's always going to be false, false, false. Now 4 of them. False, 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 false. Maybe, false, 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 false. So there's always going to be one more comparison that can never be true, because once we start putting those elements at the bottom, they'll never be wrong. So for that reason, rather than saying that this statement 4, 5, and 6, each of them is the same as this one, I'm going to say on average you're losing about half of them. So basically, so initially they can all be true, but once I have this one, it's going to be 1 less. Now it's going to be 2 less. So on average, if you have all, and then 1 less, 1 less, 1 less, 1 less, average is going to go to the middle. So I'm going to divide it in half. So it's going to be the same as this, but only half the time. In the worst case, this is going to be true. It's an approximation. Is it exactly correct? It's close. It's very, how close? Very close. The bigger the n, the closer it is. Okay, so it's reasonable. So now all I need to do is add this and this and this and this, and you can see here, this is n squared minus n. This is n minus 1 squared, which is this part, and this is 3 of these, right? Tick, tick, tick. So it's going to be 3 times this over 2. It's this. When I simplify it, I have a result which says 7n squared plus 13, I think, is that plus or minus? Minus 13n over 2 plus 5 over 2. What does it mean? It means that if I'm bubble sorting an array of 1,000 elements, I'm going to execute how many statements? 3.5 million minus 6,500 plus 2.5. Yeah, how do you do 1.5? What's an approximation? How close? Very close. So we don't worry about the half. You want to round it down? You want to round it up? Okay. Does everybody understand what this means? If I'm executing, for example, 16 statements, that's going to be 256 over 2, 128, 7 times 128, minus 13 times 128 plus 2. So this gives you instruction count. Does that make sense? So if you look at it, if n is 1,000, this is 3.5 million. This is only 6,500. If you had $3.5 million in your account, and somebody says you have to spend 6,500, you'd be like, so what? Okay, I can spend this stuff. It's not that much money. But if you have 10,000, somebody says you got to spend 6,500. Now you're getting nervous. I'm going to have no money. So this is very small. As n is increasing, this term is more significant, and this term becomes less significant. For example, suppose that n is 10,000. That's 10 to the 4th power. Right? What's 10 to the 4th power squared? 10 to the 8th power. What is that? That's 100 million. So that's going to be 100 million times 3.5. 350 million. This one is going to be 6.5 times 10,000, 650,000. Do you understand the difference? So what's going on is n is increasing. The difference between this, and this becomes huge, and really these don't matter that much. They're smaller terms. Now, we're going to change our code a little bit, because basically what we realize is if we always keep comparing all of them, by the time we're halfway through, half the elements are sorted. So that means that half of these comparisons are not even necessary. So let's just compare what we need to compare. So we'll change the code. Rather than 1 to n minus 1, we'll say 1 to n minus I. So what's going to happen? 1 to n minus I. So when I is 1, it's n minus 1. So we stop here, n minus 1 to n. But when I goes to 2, it's n minus 2 to n minus 1. We stop here, we don't do this. So we remove one comparison each pass. So doing that. So now we are going to count the statements, see if we can reduce the number of statements we're executing. So the first statement is still n. The second statement is n times n plus 1 over 2 minus 1. And you can do this yourself if you want, or I can explain it later. And statement 3, 4, 5, and 6. Now we can assume that statement 3, which is the test, can, in the worst case, always be true. For example, if the array is in reverse order, then we're always going to, every test is going to have a problem. So that can happen. Does it happen all the time? No. Does it happen typically? No. Does it happen in the worst case? Yes. Does it happen in the best case? No. Oh, okay. So what we're doing is we're counting the statements assuming the worst. Because if we assume the worst, we know we cannot do any worse than that. That's the worst case. So it's going to be at least that or a little bit better. So when we do that, and so what we end up doing is we end up getting this instruction count, which is 5 over 2n squared minus 1 half n minus 1. Notice now, if my n is 1,000, now it's about 2.5 million. Whereas before, we had 3.5 million. So when n is 1,000, we've reduced about 1 million instructions. So the performance will get better, but the complexity will not improve. Because the complexity is still n squared and is still n squared. And you know what n squared look like. N squared is a parabola, right? So one parabola looks like this, one parabola looks like this, right? When we go out here, both of them are going to be very, very high. So sometimes they start slower, but eventually they all grow to very large numbers. So therefore, since they're both still parabolas, they're still quadratic, then the complexity is the same. But the performance is a little bit better here because we will definitely have fewer instructions. But still, same order of magnitude. Still parabolic, still a parabola complexity. Okay, so now, so you can see that this is kind of a pain, right? It's a lot of algebra, blah, 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 you gotta count this. But really, do we really, if I'm telling you that this is the expression for the instruction count, but then I'm telling you this doesn't really matter, this doesn't really matter. In fact, I'm telling you that 5 over 2 doesn't even matter, just the n squared matters. Because I told you that the 5 over 2, 7 over 2, who cares? It's still n squared. So really, the most important part is that out of this whole thing is just this, the highest order term of this polynomial. So therefore, what we can do is we can basically find in an algorithm code what we call a characteristic operation. The characteristic operation will be that operation which is critical for the algorithm to succeed. And in order for us to do that, where do you think is the characteristic operation? I would say it's definitely not this, because it's a loop. I would say it's not this, that's a loop. I mean, they're important, but is that the operation that really tells you? This is really the characteristic operation, the comparison. Because when you compare, if you don't compare, that's good. For example, if everything is sorted, you don't do any comparisons, you're done. But when you have to compare, now sometimes you'll swap, sometimes you won't, but if you compare and swap, it's 4 statements as opposed to 1. So if you compare 400 times, it's 1600 if you swap every time, or 400 if you don't, same order of magnitude. 4 times something is still the same order. 4n squared is still n squared. 5n squared is still n squared. So we're going to pick one operation, which is the critical. Now, if you have a loop and a loop, that characteristic operation better be inside the inner loop, because otherwise it's not going to really do the right counting. So we need this characteristic operation. And so we're going to choose that to be a comparison. All right, so the characteristic operation of bubble sort. So we've seen for bubble sort, we have T of n, and T of n is our time, it's going to be a time complexity. That's our instruction count. T of n is an element of big O of n squared. How many of you have heard of big O notation? So big O notation is what we call an upper bound. It means that it cannot be any worse than this. Is it going to be as bad as this? Maybe, but it could be better. It's an upper bound. For example, I tell you, how much money do you make? Well, I'll give you an upper bound. $50 million a year. Do I make $50 million a year? Well, it's my upper bound. Maybe I only make $49 million a year, right? No. So, but the bottom line is, so it's an upper bound, which means that it could be as that high or lower. It cannot be higher. That's what big O means. It can be, so that means O of n squared means some constant number n times n squared, and no more than that. That means it can't be n cubed, because n cubed, the limit of n cubed over n squared goes to infinity. So they're not proportional. But the limit of 3n squared over 2n squared is what? What's the limit as n goes to infinity of 3n squared over 2n squared? 1.5. It's a constant. Because 3n squared over 2n squared simplifies to 3 over 2, because the n's cross out to be a 1. So you have 3 over 2. So that means the upper one is always 3 to 2, 1.5. So the faster function is always 1. So it doesn't go to infinity, it's always 1.5. Well, if you're 1.5 bigger than me, you're not an order of magnitude bigger than me. You're just 1.5, 2, 3, 4. You're still in the same complexity level. Okay. So we're going to do one more approach to this bubble sort algorithm. Now, remember, if I gave you an array, and this array was already sorted, and we started doing the comparisons, if we did n minus 1 comparisons, every one of them would end up being what? False. Everyone would be false. So that means false, false, false. Well, if I do a pass, and every single comparison is false, that means this is okay with this is okay with this. That means there's nothing out of place. So that means that I could actually stop after one pass and say, we're finished. And certainly if I do one pass, what's the complexity of a one pass? Big O of?
1.
Big O of? No, because there's n elements. So you have n minus n. So 1 passes big O of n. So if the array elements are sorted, and I do a pass, n minus 1 comparisons, and they're all fine, never swap, so I'm done. I did a comparison, did a complexity of big O of n. Linear, right? But if I swap once, I gotta do it again, because I don't know, I need to have no swaps before I can say we're finished. So if I do swap on the first one, I have to do it again. If I have another swap, I have to do it again. If I don't have a swap, I'm done. Now, would you agree that there's a chance that I perform, so if I take an array of random elements, let's just say 10 elements, make it small, 10 elements, random array of 10 elements, and I randomize them and I basically start the bubble sort. Is it possible that I perform 0 swaps? It's possible. And that would happen when? If they're sorted. Now, again, I'm going downwards. I'm going to do like the homework problem. Okay. Now, suppose my numbers are like this. Suppose my numbers are like this. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 and 1. 10, 2, 10 and 3. 10 and 9. So I will do 9 swaps. Now I'm going to do it again. What happens?
All false.
So I can stop after how many passes?
10 passes.
After 2 passes.
Oh.
After 2 passes I can stop. So now, can I ever stop after 1 pass? Yes. If they're sorted, I can stop after 1 pass. And I just proved to you I can stop after 2 passes also. Is it possible that I may need all 9 passes for 10 elements? Yes. And if 1 is at the bottom, then that 1 is going to come up 1, 2. So I may need all n passes. So would you agree that with 10 elements, I may need 1, 2, 3, 4, 5, 6, 7, 8, or 9 passes? Right? So the best case is 1, because I got to do 1 pass to make sure it's sorted, because I don't know if it's sorted or not. And the worst case is 9. In general, the best case is 1, and the worst case is n minus 1. So the question is, if the best case is 1 and the worst case is n minus 1, I'll just call it n because we're friends here, so we can use n. If the best case is 1 and the worst case is n, where do you think it's going to be on average? So you might think it's going to be the best case and the worst case divided by 2, and you'd be wrong. And here's why you'd be wrong. Here's why you'd be wrong. Now, so this is where things get interesting. This is why we make it a class out of this rather than just like guessing and going with our feelings. I feel very positive, I feel very negative. Okay. We can all have different feelings. We cannot have different feelings in algorithms. Algorithms have to agree, they have to be concise, they have to be mathematically correct. So let's think about 10, let's just think about 5 elements. We're going to reduce our problem. Just keep reducing it until it gets so easy. 5 elements. If the elements are in order, I do 1 pass and I'm done. Now, these elements are randomly initialized. So I randomly put values, 1, 2, 3, 4, 5. So what is the likelihood that the elements are going to be in order when I randomly initialize them? Well, the question is, let's just for the sake of do you understand that if we have 5 different numbers, it doesn't matter if they're 1, 2, 3, 4, 5, or 23, 33, 49, 127. We can always put them in order, and then we can always rearrange their order if they're all different. So with 5 elements, if I take elements 1, 2, 3, 4, 5, I can reorder them. 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3, 5, 4, 1, 3, 2, 5, 4, 1, 2, 3, 4, 5, 4, 3, 5, you understand. How many ways can I put them? Well, for the first element, I have 5 choices. Second one, I have 4 choices, 3, 2, then I'm locked in. So it's going to be 5 times 4 times 3 times 2 times 1. That is 5 factorial. That's 120. There are 120 ways I can put 5 different numbers in. So, what is the chance that my random numbers happen to be in order?
1 in 120.
1 in 120. Well, as you can figure it out, that's less than 1% chance. Let's say it's 3/4 of 1%. 0.007, 0.008. Let's just be simple. But that 0.8% represents one pass and you're done. That means the probability of one pass and done is less than 1%. But the only possibilities are 1 pass, 2 passes, 3 passes, 4 passes. There's 4 possibilities. They're not equal. Because the first one with only 1 pass only has a less than 1% chance. So that means that 99% are going to be here. So our idea of balancing in the middle, not likely. So it seems a lot more are going to require 4 passes than 3, than 2, than 1. So it's going to be heavily weighted to the back end. So we are asking ourselves the question, how many passes do we expect? And the answer is we don't know, but it's not looking good for few passes. Because the probability of 1 pass is so little. I mean, think about it. Let's say you had 100 numbers. 100 factorial orders. 1 over 100 factorial is so small. We can't even, it's just ridiculous. 1 over 10 factorial is 1 over 3.6 million. 1 over 100 factorial is probably 0.0. It doesn't even, and that's 1 pass for 100. How about 1,000? 0. Okay, is it really 0? No. Nothing is ever 0. Nothing ever has a 0 probability. If you had 1,000 elements, the probability of randomly initializing them and them being in order when they're all different numbers is 1 over 1,000 factorial. That number probably has, 55 trillion zeros before you hit the number. So it's just not going to happen. Could it happen? Yes. Are you going to bet all your salary for next week with me on that? I hope so. No, you're not going to do that because you're going to lose. Is it certain? No. I'm certain I'm going to win though. Okay, because that's how things work. So probability is a powerful thing. Nothing ever has 0 probability, but certain things are so unlikely that we will bet lots. Okay? We know certain things are unlikely. We can send people into outer space saying this could happen, but the risk is so low, we're going to take that risk. Okay, so probability is an important thing that we have to figure out. So you can see that here, what we're doing is we're changing the code just a little bit. We're going to call pass number 1, just count the passes. And then we're going to say swap is true. We're going to say every time we swap, we have to do a pass. So initially, since we need at least 1 pass, let's make swap equal to true to force the first pass. So swap is equal to true, while swap, true, and pass is less than n-1. That means we haven't done enough of them, right? Make swap false, because now we're going to have to reset it to true again, because maybe we don't swap on this pass. So make it false, and then do all this stuff. If we ever have a mismatch, we swap, and we set swap to true, so that next time we do it again if we need to. So if we set swap to true, and then to false, and we never swap, it stays as false, and then we're out after 1 pass. So the question becomes, what is our expected number of passes? Because we know the best case is 1, we know the worst case is n-1, but we are now doubting that the average case is going to be in here. Let me ask you a question. So I need a calculator. Calculator. You ready? Okay. So let's count the probability that we will require the most passes. So we're going to go back up to 10 numbers. Okay. So with 10 numbers, somebody made a mess of my board. Who was it? All right, we didn't see anybody. Okay, so let's say n is equal to 10. N is equal to 10 number. Now remember, 10 is a very, very small number, right? So we know the probability of 1 pass is going to be equal to 1 over 10 factorial. Do we know that? We agree on that, right? because that's only one out of all these orders of 10 at random that's going to be in order. So, Karanvir, you can tell me what is 1 over 10 factorial? And you can give it as a decimal. How many zeros?
6.
What you do is you do 10 factorial, and then you do 1 over x. Got it yet or not yet? Do you have a factorial button on the calculator?
602756.
Got it. How many zeros? You don't have zeros? Okay, who's got it?
60.
Go ahead. 3, 4, 5, 6,
2756.
2756. Okay. That is the probability that you require 1 pass. Probably 1 pass. Now let's look at the probability of 9 passes, because that's the worst, isn't it, right? Everything else is in the middle. So let's think about it. What would it take for it to be, if we're going like this, to be the worst case? Well, the worst case would occur when the smallest number is at the bottom. When the smallest number is on the bottom, after 1 pass it goes up 1. Second pass it goes up. Now, so let's say the numbers are 1 through 10. So basically, I have an array of 10 numbers. I have an array of 10 numbers, and the smallest number 1 is at the bottom. And do I care what's up here? I do not care what's up here, because I know after 1 pass that 1 is going to be only rising 1. So how many numbers are here? 9. And how many orders can I have 9 numbers? 9 factorial. So what I have is, so I have 9 factorial divided by 10 factorial. So what is that? 0. So that's going to be equal to 9 times 8,765. This is 10 times 9, so it's going to be equal to 1/10, right? So 0.1. So this is how much more likely? 1, 2, 3, 4, 5, 6. This is 1,000,000 times more likely than this. Okay? Now, is this correct? Is probability of 9.1? We basically said that the lowest number has to be at the bottom. What if the lowest number is not at the bottom? Can we still have the worst case?
Smallest number at the highest.
Could we still have the worst case if the smallest number is not at the bottom? Yes?
Take the highest in the beginning.
Well, the highest in the beginning, because we're comparing down, highest will take down immediately. So let's just use this as well. Now, let's think about what will it take to have the probability of 8 passes. So now, what we could have is we could have the smallest number not at the bottom, but second to bottom, or we could have the second smallest number at the bottom. Or both. Okay? So now we have to start doing some complicated combinatorics, adding these things together. We're not going to solve this problem right now, but I just want you to think about the fact that the average number of comparisons is not going to necessarily be in the middle. The average is not in the middle because the probabilities for all cases is not the same. So that's important to understand. Okay, so you get that. So the question is this. Is this a better algorithm than, let's say, this one? The j I to n minus I. Is this a better one? Is this going to be better? Well, if the worst case tends to happen, if the worst or almost worst tends to happen more often, or typically, or normally, then this algorithm is kind of bad in a way, because now the test is twice as long. There are two instructions here. I have to test this condition to be true and this condition to be true, this one, and the logical and of this one, and then when I swap, I always have to do an extra statement. So actually my instruction count is increasing in the worst case, but it's better in the low cases, but what's the likelihood of those things? And again, it's like, well, it's not so obvious. It's not a trivial question. The bottom line is, we don't know. Now, give me a situation where this algorithm is better. Give me a scenario. You're working in a company and you say, I want to go with this algorithm over the other one because it's better. Why? Tell me why. Tell me the scenario that it could be better, because it could be.
Only sorted elements are
Partially sorted.
Be careful of partially sorted, because remember, if I have my smallest element here, this is pre-sorted. 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. I mean, it's pretty sorted. So what we can say is, I would say use this algorithm if for example, 90% of the time our data comes in sorted. How do I know that? Because I work in this company. We've done the analysis. We understand how that. Okay, so in that case, on average, you could get some type of. Now, of course, I'm your boss. I'm going to say don't use double sort. It's a real company here. We're not playing games, okay? But what I'm saying is that this algorithm could only be true if certain conditions were true, if you knew something about the data. So certain algorithms might be okay under special circumstances, but not necessarily under general circumstances. Okay, so what this leads us to is that our analysis of algorithm is going to be divided into 3 views, which is the best case, the worst case, and then most interestingly, the average case. And the best case, basically, if we look T of n, remember T of n is our instruction count, right? So T of n. Now, what we're going to do is we are going to assume that the algorithm is operating on n elements. Now remember, when my numbers are in one order, my T of n is one number, because more comparison, more truths, so more swaps, fewer swaps, right? More in order, less swaps. Okay, so what happens is that even though I have n numbers, Ti of n could behave differently for different orders of these n numbers. So that's what this I represents. I'm going to say there are k possible instances or classes of input that will be n. For example, let's say my data is 1, 2, 3, 4, 5. That's the same class as 1, 2, 8, 13, 29. Because the numbers are different. Okay, but even if the numbers are the same, for example, let's say I have 1, 2, 3, 4, 5, 1, 2, 4, 3, 5. Well, no, 1, 2, let's do 1, 2, 1, 3, 4, 5, 1, 2, 4, 3, 5. They're going to both end up having the same number of swaps necessary. So what I'm saying is that even though I have 5 factorial orders, some orders of the same numbers will require the same number of swaps. How do I know that? Because when you have 5 numbers, you will have 1, 2, 3, or 4 swaps only. But the number of orders is 120, right? So the number of permutations is 120, but the number of swaps, all of those 120 will have is either 1, 2, 3, or 4. So I know that the number of, that there are only 4 classes of when n is equal to 5. Does that make sense? So that's what this represents. This represents basically from all these n numbers, there's only k classes, and each class for each level of I within 1 to k, they will require the same amount of work. So what we're saying is that each of these k's have a little bit of different work. That's why we have to use all the values from 1 to k. So I goes from 1 to k, and then we look at the actual instruction count for that ith instance, and we take the smallest of that. That's the minimum. That's the best case. So min of that is the best case, b of n. That's the best case performance, best case instruction count with n elements. The worst case, we do the exact same thing, but we choose which one? The one with the worst case. So we choose that one. But the average case is the most interesting. Basically, we look at all the cases, we add them up, but we multiply them by the p of I, which is the probability of happening. So we multiply the work times the probability of the work. So I'll give you an example. We'll just make one up, okay, shall we? So I'll just make up an example. So let's say we have, let's say b of n is, well, let's say b of n is equal to, let's say is equal to 2, and worst case of n is equal to let's say, 100. Okay? So that's a different, let's say, instruction count. And let's say k is equal to 5. What does that mean? That means there's only 5 possible amount. Each of the orders is going to be 1 out of 5 complexities. 1, 2, 3, 4, 5. So what we're going to do is we're going to sum, as I goes from 1 to 5, the probability of I times Ti of n. So I'm going to go from the best case to the worst case. So let's say the best case is I is equal to 1. The worst case is I is equal to 5, just making that up. So therefore, I'm going to say, for example, so it's going to be equal to, let's say the probability of the best case is, let's say it's going to be 1%. So it's going to be 0.01 times 2. Let's say the probability of the second, let's say best case, is going to be 4. So it's going to be 0.04 times, and let's say that complexity is equal to, let's say, 4. And then we're going to have probability of the next one, say, is going to be 8%. Let's say the work is going to be equal to 10. Plus the next one is going to be the fourth one. Now let's say the probability goes up to 20%, 0.20. Let's say the work is going to be 15. And finally, it's going to be the probability of the worst case. Well, since this is 1, this is 5, this is 13, this is going to be 23, 33. That's going to be what? That's going to be 67%, right? Times 100. Why 67? Because the probability always has to add up to 1.0. If I only can have case 1, 2, 3, 4, 5, what's the probability of 1? Okay, what's 2? What's 3? What's 4? Well, if you add up these 4 probabilities, 100% minus these is this remaining one. And you see I got 33%. Probability, 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 33%, it's got to be 67. So when I multiply and add the probability times the time complexity, that will give me the average. Make sense? Okay. So let's look at a simple example where we can demonstrate how that is being actually computed. So what we're going to do is we're going to look at a linear search. We're going to look at a linear search of an array. So we're going to assume that we're searching an array. Array, you can think of the array as just basically locations like this, right? So we're looking for a particular value, x. And if x is equal to the first one, we say success. If it's not equal to the first one, we look at the second one. If it's equal to the second one, we success. We're done. So if I fail and I succeed, my instruction count is 2. If I succeed right away, my instruction count is 1. If I have n elements and the element is not an array, then I will make n comparisons, and my instruction count will be n, and I will fail, but I will at least have an answer. Okay? If the element is at the end, is the last one in the array, what's my complexity to do that? What's my instruction count? n again. But my result is I found it. But if it's not there, it's going to fail, 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 n, and I didn't find it. So what I have here is I simply look at the instances. So basically the instances are, if I have n elements in the array, the first instance is that x equals the array element in position 1. The probability of that is p over n. Let's say the probability of finding the element in the array is 100%. And let's say there are n elements. So if you take 100% or 1.0 divided by n, 1 over n is the probability of that element being in the array. Okay? And how much work do I do to match the first element? 1 comparison. That's 1 comparison. If I fail this one, and I match it on the second one, the probability of matching it's still the same here, but now I've done 2 units of work, 2 comparisons. And finally, if I match it on the nth one, that means I did not match them earlier. That means my number of comparisons is equal to n, and my probability is 1 over n. Why 1 over n? Because I said the probability of finding it is 1.0. So what I'm saying is 1 over n means that it's equally likely to be found in any of the locations in the array. So if I have 10 locations, I'm saying the probability of this element being here is 1 over 10, 1 over 10, 1 over 10, 1 over 10. That means it's someplace. Is it here? Maybe. Is it here? Maybe. Maybe. Maybe here. But it's someplace. It is someplace. But if I told you the element in 10 element of array, the element may not be there. I said the probability is only 50%. That it's in the array anywhere. So you take 50%, 0.5, and you divide it by 10. So 0.5 divided by 10 is 0.05, 0.05, 0.05. Get the idea? So that's why I'm talking about P over N, because P over N is the probability it's in the array divided by the number of locations in the array. Now, if I don't have the element in there at all, then X is not an element of the array anywhere 1 through N. And the probability of that is 1 minus P. 1 minus P. So if P was 0.5, 1 minus P is also 50%. If P is 60%, then this is 40%. If P is 30%, then this is 70%. The amount of work I do on a failure is N. I compare everybody and I fail. Here, I compare everybody and I succeed on the last one. So, notice that the K value, our K value, is equal to N plus 1. Does that make sense? Anybody understand why it's K plus 1? Why N plus 1 is K? Because these are the classes that can happen. Match on the first, match on the second, match on the third, match on the last, don't match at all. There's N minus 1 things that can happen. That's it. You can take any number of arrays, put N elements in them, mix them up, look for an element. One of these things is going to happen. And we're making the assumption that the probability is the same in the array and 1 minus P, that it's not there at all. Questions?
Excuse me, Professor.
Yes.
The last one, can we go by it with the same analogy like you explained for the for loop, that after the nth trial it will go for the n plus 1th trial, and then
There is no N plus 1 trial.
yeah, that's when it will
Because, but it isn't, so the N plus 1 trial is basically, remember, so what we're doing is, let's say we have 10 elements. So if we're going to fail to find it, we're going to look at the first, look at the second, third, fourth, fifth, sixth, eighth, ninth, 10th. This is the last comparison. If we haven't found it in 9, we're going to compare 10. It's either going to be succeed or failure. We're done. There's no more work. So the amount of work on matching the last element
Has to be N.
and match or not matching one at all is the same amount of work. So what we're going to do is we're going to use this approach. We're going to go from 1 to N plus 1, which is the number of possible things that can happen in all the ways that elements can be configured, multiplied by the sum of the product of each instance times the time complexity in terms of instruction count of that instance. And so what we have is K is N plus 1, so we're going to go from 1 to N plus 1, Pi times Ti of N. And we notice that when you go from 1 to N plus 1, you can split it to 1 to N, and then we can take that last N plus 1 and just pull it out here. And the reason I'm doing that, why am I pulling out this term from this summation?
All the probabilities
I'm
are
pulling it
same.
out because the probability here is 1 minus P, but here the probabilities are the same. So I'm pulling it out because I'm trying to simplify it. Okay, so what I'm going to do is once I do that, then what I have is notice that Pi from 1 to N is always the same. So that's why I can now, instead of saying Pi, I can just say P over N. But P is a probability, N is a constant, so therefore the P and the N can come out in front of the summation actually. So you have the summation of I times P over N. Summation of I from 1 to N is N times N plus 1 over 2. And we'll go over that for those of you who don't remember that. So it's going to be N times N plus 1 over 2. And P over N is P over N. And guess what happens to the N's? They cross out. So that's a simplification here of the first summation. The second summation is when the probability of the N plus 1 case. That's 1 minus P. So 1 minus P times the work for that one, which is N. So we have 1 minus P times N, so just 1 minus P times N. So when we simplify it, it's P times N plus 1 over 2 plus 1 minus Pn. That's the average complexity of that algorithm. That's the average complexity of that algorithm. So let's see what that really, how that P really plays out. If P is equal to 100% or 1.0, that means the probability of the element in the array is certain. That means that P is 1.0 and 1 minus 1.0 is 0. So that means that the average, so if the element is definitely in the array, then the complexity is going to be N plus 1 over 2. What does that mean? If it's in the array, you're on average going to be working half comparisons. On average, you're going to be at the half comparisons. If the probability of the element in the array is 0, then this is going to be 0. It's going to blow this whole term out to 0. 1 minus 0 is 1. So that means if it's not an array, you're doing n work. Get it? Okay. So basically, this is the expression for an arbitrary p. Now remember, p probability of the element in the array is no less than 0 and no more than 1.0. Probability is always here. You cannot have a probability more than 1. You can have a probability of negative. Okay? 0 to 1 inclusive. 1, what does it mean when something has a probability of 1.0? Definite or certain. What has a certain probability? Very few things. We think the sun will come up tomorrow is certain. That's nice thinking. It's always worked before. My grandfather said it was true. My father said it was true. It must always be true. But we know, down the line, at some point in time, it might not be true. But we're still banking on it to be true, like certainty. But it really isn't. So very few things are actually certain that they can happen or they must happen. What's the probability that you will get an F in the course and you come to every class? It's not very certain, not very likely, but you could be the first one. You never know. You never know. Okay, everybody understand what I'm doing here? So this is an important result. This tells us this is the average probability under the assumption of the element being there equally likely in here. Of course, we could have a different assumption of probability. Maybe our assumption of probability is that it's less likely here and it gets more likely towards the end. Then our equation would be a little bit different because our assumption will be a little bit different. But I think making an assumption of equally likely is reasonable and it makes our analysis a little bit easier, a little bit more straightforward. So now what we're going to do is we're going to look at one more variation of this average complexity, and that is looking at this algorithm from a different standpoint. Let's say we have an array, and this array is still n elements, but this time the elements are in order, so they are increasing. So let's say they're increasing 10, 20, 30, 40, 50, 60, 70, 75, 88, blah, blah, blah. Okay, so I'm looking for 27, 10, no, 20, no, 30, no, but I don't have to go any further because they're increasing. So I'm looking for 27, this is 30, I can stop. So now I can fail, not at the end of the array, I can fail anywhere. If the first number is 10, I'm looking for a 5, not a match, fail. So that means failure can occur with one comparison or with n comparisons anywhere. So what happens is the number of cases changes. Basically, what we can have is, rather than having n plus 1 cases, we have n plus 1 successes and n plus 1 failures for a total of 2n number of cases. So k is now equal to 2n. So this is the first n instances are where we match on the first through the nth element. And the next n cases are where we mismatch and stop because we fail early. Okay? Now the amount of work we do here on success is the same as before, but the failure always had a complexity of n, but now failure is also going 1 to n because we can mismatch and fail, mismatch and succeed because the data is sorted. So now our solution is going to be a little bit different. So we're going to look at this one. Let's take a look at how this looks. So what we're going to do is we're going to say the average complexity is going to be 1 to 2n because k is the number of ways the algorithm can proceed. It can stop on a success, it can stop on a failure. Anytime. So 1 to 2n, pi ti of n. That's just the model of the average complexity. And so we'll write this, we'll split it into 1 to n, and then n plus 1 to n to 2n. Do you understand why I did that? And again, I did it because, okay, I've split them into successes and failures. So here, what I have is, this is always going to be p over n, because for these cases, it's always p over n, summation of I. Does everybody know why it's summation of I? Because this is successes. Compare 1 succeed, you did 1 unit of 1 work. succeed on the second one, that means you compared the first, failed, succeeded on the second one, you did 2 units of work. So that's why it's always the same. That's why. So now, this one is going to be 1 minus P over N. If you look over here, so failures, I got to make it a little bit. So here, notice that P over N, the probability of success was spread evenly across all the elements, but 1 minus P now had to be spread evenly over that, right? So the probability is equal to 100%, then it's going to be 1 over N everywhere and 0 everywhere here, because you can't fail. But if the probability here is, for example, 70%, it's 70% divided by N and 30% divided by N. These are the probabilities. Okay? So what we have is the P of N has the probability of successes, and 1 minus P over N has the equally likely probability of failures here. And I is going to go from it should be N plus 1 to 2N.
Yeah.
Sorry, not I plus 1, but N plus 1 to 2N. So now I simplify this, and so what I did here, I simplified it so that N again cancels, so it's going to be P times N plus 1 over 2. And this I simplified to 1 minus P over N. I changed this summation from here to here. Let's see how I did that. Now, look at this summation here. This goes from I plus 1 to 2N. When I is equal to I plus 1, how much is I plus 1 minus N?
N plus 1
And
minus
that's
N,
N
right?
plus 1 to 2N.
Okay, so when I is equal to 1, this is equal to 1. Sorry.
N
Yeah,
plus 1.
sorry. So this should be equal to N plus 1 to 2N. So that means that when I is equal to N plus 1, it's N plus 1 minus N, which is 1. So when I is equal to 1, it's 1. When I is equal to N plus 2, N plus 2 minus N is equal to 2. When I is equal to 2, 2. So what I did was I added or subtracted N from here, and I added N to here. So I basically subtracted N from here, and I added it here to balance out the equation. If you lower the index, you can increase the use of the index by the same amount, and you balance out the summation. Okay, so I have this. So now, from here, I get P times N plus 1 over 2 plus 1 minus P. And this is, again, going to be N times N plus 1 over 2. N times N plus 1 over 2. And the two N's will cancel, so I get P times N plus 1 over 2 plus 1 minus P times N plus 1 over 2. When I take everything out, the P completely drops out, and the final answer is N plus 1 over 2. Which means that actually it doesn't matter what the probability is, because of the fact that you can succeed anywhere equally likely and fail anywhere equally likely, so therefore you're going to, on average, do half the work, no matter what the probability is. Does that make sense? Maybe yes, maybe not, but that's what it comes out to be. So if we look at these cases, so now what we can do, and I'll try to do this very briefly, is you can take a look at it more yourself, and this is very important actually. So what we have is we have the first result, right, where the array is not ordered, so array is unordered, and here we have array is ordered, so we can stop early on a failure. And so what we have is average complexity here and average complexity here. And I'm setting average of the first one bigger than average of the second one. By setting an inequality, I'm going to solve the case for when this algorithm is worse than this one. Because when you are bigger, you have more instruction count, you're worse. So when I solve this inequality, I'm saying, when is this worse than this? So when I multiply this out and I simplify all this stuff out here, I end up going from here to here to here. Finally, I have P plus 2n minus Pn greater than n plus 1. Then I'm going to have P minus Pn greater than 1 minus n. And then I have P times 1 minus n. I factor it out. It's greater than 1 minus n. Then I'm going to divide by, I'm solving for P, I'm dividing by 1 minus n. But since n is a large number of size, and 1 minus n is going to be negative. When I divide a greater than by a negative, I get switching of the sign. The sign switches. So greater than becomes less than, and the solution is P is less than 1. So the P less than 1 is the condition when this algorithm is worse than this, or this is better than this. this is smaller, so it's better than this one when probability is less than 1. What does that mean? So when it's less than certain that the element is in the array, then this one, early stop, the second one, is better than this one. Now, if I switch the order and I said, okay, when is this one better? So I would make less than, 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 greater than. So this algorithm, the first one is better when probability is greater than 1. When is that? Never. So it's never better. And if I said, when are they the same, I would put an equal sign here. Equal, 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 equal. They're the same when probability is certain. The first one is never better, and the second one is better when the element may not be in the array, when it's less than certain that the element is in the array. So we can make a comparison about the average behavior of two algorithms this way. And simply, if I give one average behavior, another average behavior, I say, when is this one better? It's better when it's less than this one. So set it equal to less than, solve it, simplify it, and describe the condition. This is very important that you understand to describe the condition. Okay? We're going to stop here. Can we stop? I think it's time to stop.